Have you ever wondered what existed before the first second of the universe? Not just before humans, not just before Earth, but before time itself had any meaning. Today we're diving into one of the most mind-bending questions science has ever attempted to answer. How did time actually begin? I'm talking about a journey that starts at a moment so incredibly brief that our normal understanding of reality completely breaks down. We're going to explore the Planck epoch, venture through cosmic inflation, witness the birth of particles and forces, and discover how humanity went from tracking shadows on sundials to building atomic clocks so precise they wouldn't lose a second if they ran for millions of years. But here's what's really going to blow your mind. The story of time isn't just about physics and mathematics. It's about understanding our place in a universe that's been keeping perfect time for nearly 14 billion years, and how we tiny humans figured out how to measure something that technically didn't exist until the universe created it. So buckle up, because we're about to embark on the ultimate time travel adventure, and trust me, by the end of this video, you'll never look at your watch the same way again. Let's start at the absolute beginning, or as close as we can get to it. Picture this. Nearly 14 billion years ago, everything we know, everything we can observe, everything that has ever existed was compressed into a region smaller than a proton. We call this moment the Big Bang, but that's actually a pretty terrible name because nothing exploded in the way we normally think of explosions. Instead, space itself began expanding, and with it, time began its cosmic journey. But here's where things get really weird. In the first fraction of a second after this cosmic beginning, we enter what physicists call the Planck epoch. This lasted for an almost incomprehensibly short period, 10 to the negative 43 seconds. To put that in perspective, there are more of these Planck time units in 1 second than there are seconds that have passed since the Big Bang began. During the Planck epoch, our current understanding of physics completely breaks down. The four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single force. Temperature reached levels that make the core of the hottest stars look like frozen tundra. We're talking about temperatures of 10 to the power of 32 Kelvin. But here's the crucial point. Time, as we understand it, was just beginning to have meaning. Before the Planck epoch, our current theories of physics simply can't describe what was happening. Time, space, matter, and energy were all emerging together in a cosmic dance that we're still trying to understand. As we move past the Planck epoch, something extraordinary happens. The universe begins what's called cosmic inflation. In a period lasting from about 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, the universe expanded exponentially. We're talking about expansion faster than the speed of light, which is possible because space itself was expanding, not objects moving through space. This inflationary period is crucial to understanding time because it's during this phase that the universe became large enough and cool enough for the fundamental forces to begin separating. First, gravity split off from the other forces. Then, as temperatures continued to drop, the strong nuclear force separated from the electro-weak force. Think of it like water freezing into ice. As the universe cooled, the unified force field that existed during the Planck epoch underwent phase transitions, creating the distinct forces we observe today. Each of these transitions happened at specific moments in cosmic time, creating a timeline of the universe's evolution. By the time we reach 1 second after the Big Bang, the universe had cooled to about 10 billion Kelvin. This is still incredibly hot, but cool enough for the first atomic nuclei to begin forming. Protons and neutrons, which had been created earlier as quarks combined, started fusing together to create the lightest elements, hydrogen, helium, and tiny amounts of lithium. This process, called Big Bang nucleosynthesis, created the cosmic background of elements that would eventually become the building blocks of stars, planets, and life itself. But more importantly for our story, it established a cosmic timeline that we can still observe today through the abundance of these light elements throughout the universe. For the next several 100,000 years, the universe continued expanding and cooling, but it remained opaque to light. Free electrons scattered photons in every direction, making the universe look like the inside of a dense fog. But then about 380,000 years after the Big Bang, something remarkable happened. The universe had cooled enough for electrons to combine with atomic nuclei, forming the first neutral atoms. This event, called recombination, suddenly made the universe transparent to light. The photons that had been scattered for hundreds of thousands of years were suddenly free to travel through space. These photons, stretched by cosmic expansion, still fill the universe today as the cosmic microwave background radiation. Here's where our understanding of time becomes really fascinating. When we detect this cosmic microwave background with our telescopes, we're literally looking at light that has been traveling for over 13 billion years. We're seeing the universe as it was just a few 100,000 years after time began. In a very real sense, we're time travelers looking back to the cosmic dawn. As the universe continued to evolve, gravity began pulling matter together into clumps. The first stars ignited about 100 million years after the Big Bang, beginning the process of stellar nucleosynthesis that would create the heavier elements necessary for rocky planets and life. These early stars were massive and short-lived, exploding as supernovae and seeding space with the carbon, oxygen, silicon, and iron that would eventually become part of new star systems. But let's jump forward to a more familiar part of our cosmic timeline, the formation of our solar system about 4.6 billion years ago. This is when Earth's story begins, and with it, the eventual emergence of life that would one day ponder the nature of time itself. On early Earth, time was marked by the rhythm of geological processes, the cooling of the planet's surface, the formation of the first oceans, the development of plate tectonics. For billions of years, time flowed without any conscious observers to measure it. The planet rotated on its axis, creating the cycle of day and night. It orbited the sun, creating the rhythm of seasons. The moon's gravitational pull created tides that rose and fell with predictable regularity. Then about 3.8 billion years ago, something extraordinary happened. Life emerged. At first, these were simple, single-celled organisms, but they represented a fundamental shift in the universe's relationship with time. For the first time, there were entities that could respond to temporal patterns, that had internal processes synchronized with cosmic rhythms. Over millions of years, life evolved increasingly sophisticated ways of tracking time. Plants developed circadian rhythms synchronized with the day-night cycle. Animals evolved internal biological clocks that helped them navigate, hunt, and reproduce at optimal times. But it would be billions of years before any life form would consciously contemplate the nature of time itself. Fast forward to the emergence of human consciousness, probably within the last few 100,000 years. Suddenly, the universe had observers who could not only experience time but could think about it, measure it, and try to understand its fundamental nature. Early humans were acutely aware of temporal patterns. Their survival depended on understanding seasonal changes, predicting weather patterns, and tracking the movements of animals. They noticed that the sun rose and set in predictable cycles, that the moon changed phases in regular patterns, that certain stars appeared at specific times of year. These observations led to humanity's first attempts to measure and track time. Ancient civilizations developed calendars based on lunar cycles and solar years. The Egyptians created sundials that could track the passage of hours during the day. The Greeks and Romans refined these systems, creating increasingly accurate ways to measure time's passage. But it wasn't until the development of mechanical clocks in medieval Europe that humans began to divide time into the precise, standardized units we use today. These early clocks, driven by falling weights or oscillating pendulums, could measure hours and eventually minutes with reasonable accuracy. The invention of the pendulum clock by Christian Huygens in 1656 marked a revolution in timekeeping. For the first time, humans could measure time with precision accurate to within a few seconds per day. This precision enabled the scientific revolution allowing researchers to make precise measurements of natural phenomena and discover the mathematical laws governing motion, gravity, and celestial mechanics. As our understanding of physics advanced, so did our ability to measure time. The development of precision chronometers in the 18th century solved the problem of determining longitude at sea, opening up global navigation and trade. The standardization of time zones in the 19th century synchronized human activities across vast distances, enabling the coordination of railway schedules and industrial processes. But the real revolution in timekeeping came with the development of atomic clocks in the 20th century. These devices use the oscillations of atoms as their timekeeping mechanism, providing accuracy that was previously unimaginable. Modern atomic clocks are so precise that they wouldn't lose or gain a second if they ran for millions of years. This precision has practical implications that affect our daily lives. The Global Positioning System, which provides location information for everything from smartphone maps to aircraft navigation, depends on atomic clocks that must be accurate to within nanoseconds. If these clocks were off by even a few microseconds, GPS coordinates could be wrong by several miles. But atomic clocks have also revealed something profound about the nature of time itself. Einstein's theory of relativity predicted that time is not absolute, but is affected by gravity and motion. Atomic clocks have confirmed this prediction with stunning precision, showing that time actually runs slower in stronger gravitational fields and for objects moving at high speeds. This means that time on Earth's surface runs slightly slower than time in orbit due to our planet's gravitational field. GPS satellites must account for this relativistic time dilation, adjusting their clocks to stay synchronized with ground-based systems. Without these relativistic corrections, GPS would accumulate errors of several miles per day. These discoveries have transformed our understanding of time from a simple, universal backdrop against which events occur to a dynamic aspect of reality that's intimately connected with space, matter, and energy. We now know that time began with the universe itself, emerged from conditions where our normal concepts of causality and sequence break down, and continues to flow according to rules we're still discovering. Looking toward the future, our quest to understand time continues. Scientists are working on optical clocks that use light waves instead of microwaves, promising even greater precision. Researchers are exploring whether time itself might be quantized at the smallest scales, made up of discrete units, just as matter is made of atoms. We're also grappling with profound questions about time's ultimate nature. Is time travel possible? Will time eventually end? Does time flow in only one direction, or could it reverse? These questions push the boundaries of our current understanding and drive ongoing research in theoretical physics. Some scientists speculate about the far future of time itself. If the universe continues expanding and cooling, it may eventually reach a state called heat death, where all available energy has been exhausted and no more work can be done. In this scenario, time would continue to exist, but nothing would change, making time's passage essentially meaningless. Other theories suggest that time might be cyclical, with the universe eventually contracting in a big crunch that could give birth to a new Big Bang and a fresh timeline. Still, other ideas propose that our universe is just one of many in a multiverse where different regions might have different relationships with time. What's remarkable is how far we've come in our understanding, from our ancient ancestors tracking the sun's movement across the sky to modern scientists detecting gravitational waves that ripple through space-time itself. Humanity has developed an increasingly sophisticated relationship with time. We've learned to measure time with precision that would have seemed magical to previous generations. We've discovered that time is relative, that it can stretch and compress depending on gravity and motion. We've traced time's history back to the very beginning of the universe and forward to possible futures we can barely imagine. But perhaps most remarkably, we've maintained our sense of wonder about time's mysteries. Despite all our scientific advances, time remains one of the most profound puzzles in physics and philosophy. We experience it every moment of our lives, yet we still struggle to define exactly what it is. This brings us back to where we started, that almost incomprehensibly brief moment nearly 14 billion years ago when time itself began. From the Planck epoch's quantum foam to the precision of modern atomic clocks, the story of time is ultimately the story of the universe itself and our place within it. Every second that passes connects us to that cosmic beginning, to the formation of the first atoms, to the birth of stars and planets, to the emergence of life, and to the development of consciousness capable of contemplating these mysteries. When you check the time on your phone or watch, you're participating in a measurement system that traces its origins back to the fundamental structure of reality itself. The next time you watch a sunset or notice your shadow change position during the day, remember that you're observing the same cosmic rhythms that our ancestors used to first understand time's passage. When you set your alarm or schedule a meeting, you're using precision that depends on our deepest understanding of physics and the nature of reality. Time's story is far from over. As we continue to explore the universe, develop new technologies, and push the boundaries of human knowledge, we'll undoubtedly discover new aspects of time that we can barely imagine today. But one thing is certain, the quest to understand how time began has led us to some of the most profound insights about our universe and our place within it. From the birth of time in the Big Bang's first moments to the precision chronometers in your pocket, this journey shows us that time is not just something that happens to us, but something we're intimately connected to at the deepest level of reality. We are quite literally children of cosmic time, and our story is inseparable from time's own magnificent beginning.